Hello, I have already met most of you. My name is Herminso, and I'm not expecting you to be able to say or remember my family name, Villarraga Gomez, as it contains a double L and especially a double R. Those are difficult for English speakers. I still remember when I got my first full-time job in the United States, Jim Clark, my boss, then said to me, from now on, you're gonna be Mr. Gomez. Villarraga is too hard, plus it will be difficult for customers to remember it. Jim will simply introduce me as Herminso Gomez, and by doing that, he automatically killed my father. I'm not sure how much you are familiar with the Spanish surnames, but we preserve both father and mother family names. Gomez is an acknowledgement to the hard work that my mother did for me. By dropping Villarraga, Jim, my previous boss, was declaring my mother the winner of the legacy fight, and automatically delete my father's inheritance. But I actually keep both names, at least for writing. To avoid confusion, I put a hyphen in the middle to connect them. But you can just call me Herminso Gomez. At the end, Jim was right. It's easier to remember. Anyway, at this point, I think you already guessed what my presentation is about. Working. X-rays, of course. This is the topic of the main topic of this week. And I like to start this presentation with a little bit of history of X-rays. So let me go back in time to November the 8th of 1895, when this guy, Wilhelm Röntgen, discovered something he called X-ray. That was a little bit over 120 years ago, and since that date, it has changed the way we used to see the human body. X-rays became an important diagnostic tool in medicine, allowing doctors to see inside of the human body without slicing or cutting it wide open with surgery incisions. And in 1971, the first X-ray computer tomography system was created for generating 3D image visualization of the interior of a body. That was a machine designed by Gottfried Hunspel in the UK. Years later, Hunspel will receive the Nobel Prize for his invention, along with Alan Corman, who received credit for developing parts of the mathematical theory of 3D reconstruction. Again, medical applications came right after that, but also the non-destructive evaluation community started using this technology for inspecting all kinds of parts and inspect them for all types of defects like void analysis, crack detection, thin wall assessments, other kind of problems. Thickness analysis, and also to check the interior of electronic components. And around 2000, people have started to use this technology for dimensional metrology. I've been involved with this technology since 2012. I got my PhD with a dissertation in this topic and have been publishing several papers on X-ray CT metrology in journals as precision engineering. You are welcome to download them from Science Direct or just send me an email and I'll see if I'm able to provide you a copy. In X-ray CT systems used for non-destructive evaluation and metrology as well, the traditional approach is to use a projection-based geometry that is basically composed of an X-ray source, a detector, and a rotational stage to place the part. But as you hear from my previous talk, the resolution of those systems are generally limited in the best case scenario when they use the optimal settings to something around 2 to 5 microns. It's very hard to get to sub-micron resolution capabilities. Not much has been done in this matter, specifically for dimensional metrology. Until recently, we recently launched at SAIS a package to do dimensional metrology with those type of systems. And if you remember, the main difference of the so-called X-ray microscopes as compared to the traditional projection-based CT systems is that they include a set of lenses. And those lenses are going to give you the extra magnification capabilities that by changing the magnification, the optical magnification, then it's going to give you extra room for that resolution. The geometrical magnification is still there, but the advantage of the optical magnification is that allows still scan larger samples without destroying them to try to get the best resolution that you could, which will be the case of a traditional X-ray system. And this example shows how you can scan a full device, such as a smartphone, and then by using the zoom lenses of the 3D X-ray microscope, scan small regions of interest in the device. For example, do non-destructive inspection of the circuit board or microprocessor that is inside of the smartphone, and check any kind of defects like porosity inside of the VGAs that might affect the performance, the functional performance of the device. And if you increase the optical magnification, then we will be able to see at high resolution details in the microprocessor, such as the bias connections between the different layers. And using the same principle, which we can change the region and go to the different region of the smartphone and check the camera lens assembly, for example, and inspect the information that we can obtain from that that can help to improve the quality of the cell phone image quality captured by those cameras. And as a last example, you already saw a little bit of that in my previous presentation, we could inspect the battery of the cell phone to check for all kind of defects like cracked delamination or aging by charging and discharging the battery. This level of detail, scanning at high resolution, can be done thanks to the optical engine that is behind, and you can see there with the different lenses or optical magnifications that we have introduced in our 3D X-ray microscope. In practice, the measurement workflow is composed of 3 basic steps. The first, an operator selects the best settings for scanning the part based on the geometry, size, and composition. And then the X-ray system rotates 360 or 180 degrees and start collecting snapshots or image projections at different angular orientation. And after collecting several projections at those angular positions, a software reconstruction will generate a 3-dimensional model of the part volume. And this can be used to non-destructively inspect or make quality control of several types of applications from inside of the device. Now I have a question for you. Isn't 2D radiography enough? What do you think the projected image shown in the screen corresponds to? Display a hand, or maybe a globe, something like that. Let's see. It is actually a rabbit or a bunny trying to be punished. So the 2D projection can be misleading, and we know that. And we can see it from this example, and it's because the fact that you have a radiographic projections in which you have the back layers and the front layers and you might be a low density that might look like a void, but you are not quite sure. And even if you think it's a void, you don't know exactly where it is in space. So by using 3D X-ray computed tomography, then you can actually slice virtually in the 3D volume and see if those are actually voids or not, or any other kind of defect. So that's the main advantage of having 3D information. The problem of simple projections for 2D slices, then you can extract all kind of information like you see in this PCB or BGA, that you can check for solder bonds, micro bond voids, fatigue cracks, cold joints or head-on pillow, voids, electromigration, trace of any kind of defects, like you can see the broken bias, cracks, and micro cracks and the silicon features of this electronic device. Again, this level of detail is only possible thanks to the optical magnification, keeping the full device in the full integrity. You know how to slice the device. And that's thanks that you don't even have to put the sample as close as you can to the source, because you have those lens magnification, as opposed to the traditional microscopy that wouldn't allow to do that. And just to illustrate one more time with a very hypothetical example, think about this. Things about an apple. I don't want to compromise any customer part here, but this is an easy example. Just think that you want to scan the seed of the apple without opening the apple. So if you use the X-ray microscope, then you can just easily zoom in a region of interest because you have the optical magnification that is going to allow you to keep the resolution with the optical magnification. And you can see that we have several scintillators on top of the lenses that are just behind. Those are optical magnifications behind that. And after that, the visual is converted into a CCD detector into a signal that is going to a screen. If you want to do that with the traditional micro-CT using only geometrical magnification, you won't be able to do this. You will have to put the apple open to get the highest resolution of the seed. And then you extract the seed and put it as close as you could to the source. And yes, you get maybe a high resolution image, but it still will be limited to something in the order of 2-5 microns, depending on the type of system or the best conditions that you can get. It's really hard with a projection geometry like this to get to sub-micron resolution. But that's not the case with the X-ray microscope, because we don't have this type of limitation that you see there. So optical magnification and the concept of resolution at a distance are key to achieving the sub-micron resolution. This is a typical workflow. You scan the full volume of the sample, and then you using the different lenses like the 4x, 20x, or 40x, you go to different regions. You basically use a scout and zoom and get different regions and harder and at higher resolution. The example you see in the screen is use a porous glass insulator. This technique can be applied to several types of samples. For example, ceramic matrix composite, applying the same principle. The idea is basically the same. You zoom in and you can see how we get the entire sample at 14 micrometer voxel size. And using the magnification, the optical magnification, you can get regions of interest at 4.4 and even 0.4 micrometers voxel size. And you can see the level of details that you can obtain in this composite sample. The same can be done with a fiber composite sample, in which the orientation of the fiber is important and can clearly be seen in this video through virtual sectional cuts and the 3D reconstructed volume that you see over there. Additional to being able to create this nice visualization of interior features and videos, quantitative analysis can be done, such as quantification of the fiber orientation and distribution, create a color map based in the diameter and composition of those fibers. The scintillators for each objective in the X-ray microscope have been optimized to provide the best contrast. So by adjusting the lens to detect the appropriate X-ray energies at that level of resolution, we enable high contrast data as well. So this permits to get higher quality than that you could achieve with traditional flat panel detectors. And there are other applications of quality inspection of parts made by additive manufacturing. For example, without destroying the part, you can inspect at high resolution the structural integrity of the internal cavity. Check for internal defects such as porosity, impurity, inclusions in the powder material, and do measurements such as surface roughness. It is one more example of a 3D printed lattice structure made of Inconel. And you see data of two different scans, one at 8 micrometers voxel size and a small region of interest at 3.5 micrometers voxel size. The cross-sectional images, you can identify in them several interesting details of the build, such as internal porosity and the surface roughness around the joints features inside of the lattice structure. This small portion of an aluminum gear wheel made also by additive manufacturing illustrates also a little bit of this application. This has been scanned with a 3 micrometer voxel size resolution, which allows the inspection of porosity, unmelted powder particles in the finished part, and the detection of unexpected particle inclusions in the powder. All sorts of defects that might affect the functional performance of the part can be detected without destroying the part with X-ray computed tomography at high resolution if we use the so-called 3D X-ray microscopes. Inspecting the powder before the build in additive manufacturing is also important for the final product. And this is demonstrated here with a scan of a portion of powder. The more uniform the powder is, the more consistent the build. But as you can see from the picture, the morphological characteristics of the powder can be very diverse. They might come in a broad range of particle sizes, which can be a problem for melting purposes. In fact, there are some particles that already contain porosity, if you see in the bottom down. And this can degenerate in explosion during the build and create some kind of cracks in the process of generating the part. The analysis of powders can be extended also to medical devices, such as drug delivery devices. In this image, you can see a medical inhaler, where the full device was scanned for assembly inspection. And you can see in the inside, we are putting the device. And you can see the inner working components of the assembly, such as the gear and the spring part. You could do cut-to-part comparisons if you wish to do so. But the most impressive thing is that you can, if you see in the left side, you can see inside of the powder using the zoom lenses at high resolution without destroying or opening the inhaler. And this is quite interesting. Thanks to this optical magnification, you can see the morphological distribution of the powder as well. And you can see some of the particle powders that even have voids on it with more smaller particles within it. And this is possible to that system that has that optical magnification. You can move the source to detector distance and put it very close in and zoom in additionally with the optical magnification to check the powder. That's how we scan the sample. And it's published in one paper that you can check there. Again, this level of detail is possible to the optical magnification that we have in the 3D X-ray microscopes. And the full assembly of a medical device can be inspected also for a quick scan with a flat panel. You can add to this optical microscope a flat panel to make a quick scan of the full device and check the different assembly or components of the scan. And after doing the full 3D reconstruction, thanks to the high contrast capabilities that we have also in the flat panel, you can differentiate different material densities, even if they are very close one to the other. And that's allowed to make segmentation, like the one that you see in the color map, and do reverse engineering if you need to recreate a CAD model or something that you need to do your reverse engineering. This video just showed the full assembly of the medical drug delivery device, how it can be inspected with the cross sections, virtual slices that could throw the part, but the physical part hasn't been put for full inspection inside of the device. And this is one more example for industrial inspection. It's a small carburetor. A quick inspection can be performed again with the flat panel detector to see the inner working components of the full assembly, metal and plastic parts, high density, low density, and see how it fits together. But you can use then the magnification, in this case the 4X, to zoom in without putting or opening the device inside of the aluminum case casting and see how the porosity is inside there. And you see the level of detail that you can see in that is very impressive. Non-destructive inspection of rechargeable batteries is another very hot topic nowadays, as you saw in my previous presentation this past Thursday. And if you remember, if you zoom in this case with the SciSec radio ultra microscope, which can go down to 50 nanometers resolution size, you can see some of the internal particles in the battery that are split or divided in pieces in there. They have tags. By now, you probably understand what are the main advantages are of adding the optical magnification and resolution at a distance with 3D X-ray microscopy, aiming toward high resolution and high contrast. And you already seen that it's very impressive image, but the question is, okay, can we do measurements now? Can we do dimensional measurement? The dimensional metrology? And I'm asking this question because you usually see a scale in the images, but if that scale is not calibrated or traceable like a CMM, then it's not fully reliable because there is a big uncertainty that you don't know how much is. And when you are checking for high precision metrology, you need to make sure that you have high accuracy measurement. So we added more recently a metrology extension or a metrology package to this optical microscope. So now you can do that. And with this is the workflow. Basically, you have to create an artifact that is composed of Rubik's spheres that you put inside, and is very well calibrated with uncertainties that are very small, in the order of 140 nanometers, calibrated by the National Institute of Standards. We did this at MEFAS in Switzerland. And then if you want to compare, you just you calculate the CT data and plot that against the CMM data calibrated. And you can see that deviations are below 1 micron. But to give a little bit of room in terms of this has to work for several systems that we send to the field at different locations, then we provide a maximum permissible error of 1.9 plus L over 100, which if you are familiar with metrology, is the typical way to provide that in CMM. And we did this because we have experience already with the traditional metrotomes that we provide at site. We have been doing this, I think, for more than 8 years already, probably more than 10 years, providing these ways of doing calibration. And just to give you an idea, this phantom that we are using for the X-ray microscope fit in the tip of a finger. So it is really small. And this is the MP or maximum permissible error specifications that we are providing. This is one typical application example, the smartphone camera assembly, and you can do all types of measurements there without destroying the assembly. this is something that you could not do with an optical measurement system or a tactile system, because you cannot get inside of the sample. The X-ray is the only way to do it without sectioning the part. And we can do that now, not only with high resolution, but high precision metrology, because we have this accuracy statement. And the typical measurements of interest are, of course, the lenses, the fixed annular wedges, centrations, diameters, gaps, lens-to-lens tilt, apex, height, centrations, etc. And there are other examples in which the metrology extension could be applied. For example, for checking a small plastic connectors, made add-to-part comparisons, fuel injector nozzles, that if you are familiar with them, they have very tiny holes that also are very difficult to scan, impossible with a tactile probe or an optical system that you can find in the traditional market. So X-ray CT is a nice solution, and to be able to guarantee that those measurements are accurate, then if you use this workflow with the metrology extension for the X-ray microscope, then you can trust the measurement. So here are some of the main advantages of this new package. We preserve the well-known high-resolution capabilities of the 3D X-ray microscopes. This allows us to reveal the small features of the part at high resolution. And in addition, now we can do metrology tasks with the 3D X-ray microscope. This is highly repeatable, accurate, and basically we have also automated the calibration workflow, or semi-automated. Yeah, and we have the highest accuracy specification in the market. The 1.9 is the lowest MP statement that you can find among any X-ray CT metrology provider. And it has a unique capabilities that merge microscopy, high resolution microscopy with metrology capabilities. In 2 words, you can get high resolution imaging and high accuracy dimensional measurement. It is just a quick summary of 6 key benefits. Is that you have non-destructive imaging, resolution at a distance. I didn't mention, but we also have in situ and 4D imaging. The workflow is easy of use. For speed, we can add an autoloader to place a part one after the other, and now we have metrology capabilities. And the application, as you already have seen from my previous presentation, and are very diverse in different fields. And just to remember, the portfolio that we have at size is much bigger than that. Today, I have been talking about the high resolution X-ray microscope, but we have also larger systems with flat panels for metrology and non-destructive inspection, automated inspection and metrology that can be very fast, or 2D with the voxel family. So this is the one more portion of the 3D X-ray microscope portfolio that we have to offer, that includes several microscopes, even a helium-ion microscope that can go down to 0.5 nanometers. Of course, the advantage of X-ray is that you do this without destroying or slicing the part. Is the main catch. And typical markets with applications: automotive, aerospace, medical devices, electronics, additive manufacturing, and many others. With this, if you have any questions, let me know.